Hello everyone, Mr. Fawcett here, and we are back for part 2 of our 2.1 lesson. This unit is us breaking the ice into this concept of derivatives, whereas this first unit that we've done has been mainly discussing limits and the concepts surrounding those. Now there is going to be a key relationship between the limits idea we talked about in our first unit and this derivative concept we're going to talk about moving forward. In the first part of this lesson, we looked at an example, Jake driving to the store and trying to figure out whether or not he should have gotten a ticket from the cop based on how fast he was going. And the thing was, we were only able to figure out his average speed, right? So we knew his average speed over the course of 10 minutes of driving, but we weren't able to know his instantaneous speed. So if I said what was his average speed, you could have told me 30 miles an hour. But if I asked you what's his speed specifically at minute 1.4, right, you wouldn't have known how to find that, excuse me. Moving forward, I'm going to be able to give you a graph. So let's say I have a graph like this. I'm going to be able to give you a point on the graph, say right here, and you're going to be able to tell me exactly what that slope is at that specific point, right? Now, previously, the only thing that we've been able to do with regards to slope when we have a function that's a curve like this is estimate the slope. So let's say I wanted to estimate the slope on this interval, right? Well, I would pick 2 points at the ends of the interval. I would draw what we call a secant line between those 2 points, and that would give me the average slope. But it doesn't tell me what the slope is at any of these specific points along the curve. It just gives me the average. Again, moving forward within these next couple of videos and these next actually couple of units, we're going to look at tools that'll be able to tell you exactly what that slope is at that green point on our red curve. Okay, let's jump down to our next example. We are on page 3. And we are given a problem again with Jessica, who appeared in our previous video. So Jessica is trying to find the slope of the curve below at x equals c. So we're looking at this blue curve, f of t. It gives us a point, an x value c, and Jessica wants to find the slope at that specific point. So the tangent line has been drawn in, that red line, and quick refresher of what a tangent line represents. A tangent line will have the same slope of the function at the point that it intersects the function, right? So the tangent line here intersects the function at x equals c, which means the slope of the red line will be equal to the slope of the blue curve specifically at that given point. The problem is Jessica doesn't know the actual slope of the tangent line, and she only knows the one point on the tangent line. She only knows the c comma f of c point. So she cannot find the slope using change in y over change in x. Now, if that's not clear as to why she can't do that, well, let's break down that formula. So slope is equal to change in y over change in x. But remember, change in y is y2 minus y1. Change in x is x2 minus x1. So to use the slope formula, the change in y over change in x, you need 2 points on a line. Instead of trying to find the slope of the red line, she instead draws in a secant line. So a secant line touches the function in 2 spots or intersects the function in 2 points. And these are the 2 points at which this secant line intersects the function. Now, if she wants to use the green secant line to approximate the slope of the red tangent line, think about what she may need to do, right? Because right now they don't look like their slopes are very close, right? But is there something she could do to make those 2 lines look more alike, and thus their slopes be closer to one another? So take a minute to think. That's actually the answer to the question down below. And we are going to hop over to a visual diagram of this, or an interactive diagram. So I have the same diagram here. Just now I'm going to be able to move it around. So thinking about how I could move this secant line, the green line, to make it look more like the red, well, I could drag this t value closer and closer to my c value. And you notice the closer and closer that t value gets to c, the closer these lines approximate one another, right? The better approximation the secant line is of the tangent line. Now, let's quick look at what the formula for slope would be again. But this time I'm going to use my secant line. So slope for my secant line, y2 minus y1 divided by x2 minus x1. So that's going to give me, we'll use f of t minus f of c for my y2 and my y1, and then we'll use t minus c for my x2 and my x1. So that would be the formula we would use specifically for this secant line on this function. And no problem, right? We could substitute in those values and we could find the slope of the green line. But again, we're trying to find the slope of the red line. We're trying to find the slope of the tangent line. And we said as we move this t value closer and closer to the c value, the slopes become more similar, right? So for them to be the same slope, we'd have to move the t value right on top of the c value. And you can see if I do that, the lines become the same line. So we actually don't have a secant line anymore. They just both become tangent lines. Let's see why this isn't going to work, right? Because I still have these 2 points, c comma f of c and t comma f of t. But let's see what happens when I substitute those into the slope formula. So again, I get f of t minus f of c divided by t minus c. But in this case, t and c are the same value, right? So this actually changes. If t is really c, this just becomes f of c minus f of c, and we get c minus c. And you can quickly see that this is going to give us something that isn't an answer, right? This is just an indeterminate form. It doesn't mean that the slope of the red line doesn't exist, right? It just means that this method, just substituting in these values into our slope formula, is not going to give us an appropriate answer, okay? We wouldn't say the slope is undefined, right? Because we can clearly see that the slope does exist, and it's going to be a real number for the red tangent line. But this method just isn't appropriate to try to find that slope. Let's think about this problem from a slightly different angle. So let me get rid of this, and let me move my secant line farther away from my tangent. Okay. So I may not be able to figure out the exact value of the slope of the secant line when my t and c values are the same, which means I'm unable to use that method to find out the slope of the tangent line. But let's think back to Unit 1 and this idea of what a function is approaching. So the secant line, right, it's approaching, I got to move it from down here. It's approaching the slope of the tangent line, right? And you can see as it approaches from either side, it's approaching the same value, right? Whether I approach from the left, right? When I approach from the left, it's beginning to look more and more like the tangent line. Same thing as if I approach from the right. If I approach from the right, it's also approaching the slope of the tangent line. So this should hopefully trigger an idea in your head, right? When a function approaches the same value from both sides, we have a limit, right? So we may not be able to use our slope formula to find the exact value of that tangent line slope, but we could come up with something like this. We could say the limit as x approaches, sorry, not x because we're using t's and c's. So we could say, you know what, let me write the original that I erased first. So initially we had y2 minus y1 divided by the quantity x2 minus x1, and we had f of t minus f of c divided by the quantity t minus c. Now, this didn't work because we were trying to find the specific value, but we are able to find the limit as t approaches c of this quotient, right? Because the secant line has a slope. Let's do minus there before c. The secant line has a slope whenever t does not equal c, right? So as I approach from the left, the secant line is defined. The slope of the secant line is defined. When I approach from the right, the slope of the secant line is defined. So the limit of the slope of the secant line as t approaches c exists. We just can't find that value using our slope formula. But if we throw the limit notation in front of it, then we will see we're able to get an answer. So again, we're bringing back this idea from Unit 1 to help us move into our derivatives section. But there's always connections between these calculus concepts, right? And just because we finished our unit on limits, that doesn't mean those ideas aren't going to show back up again in future units. And you can see first lesson back, we're using that limit idea to look at to introduce another calculus concept. Let's go back to our notes real quick. Make sure we have everything filled in. So question 2 was just our equation for the slope of that secant line. And if we forget, remember that m just represents slope. And this was our equation, the y2 minus y1 divided by the quantity x2 minus x1, our f of t minus f of c divided by the quantity t minus c. And we said this would best approximate the slope of the tangent line when t was equal to c, right? When we moved those 2 points directly on top of one another, the green and the red line were indistinguishable. They looked the same. While we could do that on the graph, we couldn't do it with the equation, right? Because we ended up getting an indeterminate form. We got an indeterminate form as our answer. Right, 0 divided by 0. So we knew that there certainly was an answer to what the slope of the tangent line was, but the method we were using wasn't working efficiently for us or effectively. So number 5, while we may not be able to evaluate the slope formula at that specific point, we can figure out what the slope of the secant line is approaching as it gets closer and closer to resembling the tangent line. And we talked about how this was related to one of our big ideas from Unit 1. As we move the points on the secant line, one last time we'll do this. So as I moved the t value closer and closer to c, as I approach c from the left, the slope of the secant line approached the slope of the tangent. And it approached, the same thing happened when we approach from the right, right? As we move this way, the secant line slope is still approaching the slope of the tangent line. So and this gets right into what we're doing with derivatives, right? This is how one of the ways we can find a derivative is we find the limit of the slope formula, right? We can't evaluate the slope formula directly at that point because we get an indeterminate form. Our numerator and denominator are 0. But what we can do is find the limit of the secant line slope as it approaches that point. And that right there is the foundational concept of what a derivative is. Let's move back and finish number 5 off, and then we are good to go for this video. So again, we weren't able to use the specific slope formula, but we could evaluate. That's not how you spell evaluate. Still not how you spell evaluate. That's going to be close enough. We could evaluate the limit as t approaches c of f of t minus f of c all over the quantity t minus c. And like I was just saying, we're going to see in future videos, this is one definition of this word I keep throwing around, of a derivative. A derivative is just a way to find the slope of a function at a given point. And to do that, we're going to find the limit of the secant line as it is approaching the tangent line. All right, this has been Mr. Fawcett. I look forward to seeing you for our next lesson. Until then, enjoy the rest of your day.